All right, so we're going to start doing calculus with parametric curves. I'm sure everyone's excited about that. So let me go ahead and start. So basically, the idea is in normal calculus, we're taking the derivative of the dependent variable with respect to the derivative of the independent variable. And that's fine. We're going to do that here too. We're going to take derivatives with respect to the parameters as well. But we want to add a little bit of a little twist, okay? We want to talk about how the different dependent variables might interact among themselves, okay? So that's an important aspect too. We want to know how is y going to change with x when they both depend on the underlying t, okay? So let's start. Let's pretend x equals f of t and y equals g of t. By the way, I like to use the word pretend where most math teachers or notes would say suppose. The reason is because this is play. We really should, like, I want you guys to think about math as like playtime. I know, little kiddish, but it is. If you think about it as playtime, it'll be a lot more enjoyable for us, just to start. So x is f of t, y is g of t. So now let's take dy dx. So our dy dx, which we know as the derivative of y with respect to x, that's actually not going to be too difficult. We're going to take that as dy dt divided by dx dt. Okay, and it's not super great to do, but it still works. Okay, so that's really going to end up just being f prime of t over g prime of t. Okay, good. Let me put this over here. String of equalities. Okay. Next, let's take a look at the next derivative, the second derivative. That one's a little bit trickier. Okay. The second derivative of y with respect to x. Okay, or y double prime of x. That's going to be dy dx, I'm sorry, d dx of dy dx. Okay, that's nothing new here, right? Nothing new here. But now, what's dy dx? And what's d dx? Okay, d dx has this little d dt in there. So this is going to be, I got a little bit off here, so this is going to be d dt of our dy dx divided by dx dt. Okay, so what am I doing here? I'm actually just doing the same thing as before. Okay, another way to think about this to sort of what maybe work it out is think this is dy prime dx. So this is going to be dy prime dt divided by dx dt. If you think about it that way, then this makes perfect sense, right? Okay, so now let's go ahead and do this for an example. Okay, so let's take let's start with our circle. Okay, let's start with our circle. Let's take x of t is cosine t, y of t is sine of t. Okay, so let's take dy dx. dy dt divided by dx dt, that's going to be derivative of sine is cosine of t. Derivative of cosine is negative sine of t. Okay, so far, oh good. So far, so good, right? Let's write this as negative cotangent of t. Okay, now let's go ahead and do this again. Let's take the second derivative. That's going to be the derivative with respect to t of negative cotangent of t divided by dx dt. So the derivative of cosine is again negative sine. Okay. Derivative of cotangent itself is what? Cosecant squared, right? Yes, cosecant squared. So that's going to be negative cosecant squared of t divided by negative sine of t. That's going to be 1 over sine cubed of t. Okay, it doesn't really tell us too much. Okay, but let's take a look at the picture, at the graph. Okay, we know our motion around the circle is a circle. Starts here, goes in this direction. Okay, what are a couple things we notice? Okay, well, cotangent of t, that's undefined when t equals 0 and pi. So our first derivative is undefined here and here. It's 0 when t equals pi over 2 and 3 pi over 2. Okay, and here, what's dy dx? Is it increasing or decreasing? Actually, it's decreasing because as you increase in x, your y is going to go down. Okay, so let's look at that from a chart perspective. Okay. Our derivative is negative cotangent of t. Let's see what that looks like. Okay, negative cotangent of t. Okay, again, it has asymptotes at 0 and pi. Let's just do the first sort of bit, okay? Now, cotangent of t normally goes down, but since this is cotangent of negative, it's going to go up. Is that right? Yes. Let me look at a graph real quick of that. Oh, I'm just going to go with it. Okay, that's how negative cotangent of t looks. Now, remember, before pi over 2, this point here is pi over 2. So as we move, now here, this is in t, but this is for these t values. So t values being between 0 and pi over 2 are here. Those t values are between pi over 2 and pi. Okay, so here, our derivative should be negative. That means as you increase x, your y is decreasing. as you increase in x, right, as you go in this direction, your y is decreasing. So remember, this is about the derivative of y with respect to x, not the derivative of y with respect to t, which is different, okay? So what I'm trying to say is that even with these parametric equations, you can use these formulas that I gave here earlier, and this one, to determine how y changes as x changes, not as how t changes, okay? How t changes is easy. You just use the direct formula. But we also sometimes want to know what happens as the two dependent variables change, okay? How does one change affect the other, okay? All right, let's do one more. We're going to take x of t is t cubed minus 12t. Y of t is t squared minus 1. And we're going to ask, when is the curve concave up? Remember, concave up, that means that the second derivative of y with respect to x is greater than 0. Okay, so we're going to go ahead and do that. So first thing we need to do, dy dx. dy dx is dy dt divided by dx dt. Make sure I did that right last time. Yes, okay. dy dt here is 2t divided by dx dt, 3t squared minus 12. Okay, so this is y prime of x as a function of t. I know it's crazy, but that's what it is. That's y prime of x. Okay, that's a formula for y prime of x at a given t value. Okay, so now we got to find d2y dx squared. Or dy prime dt. I'm sorry, dx. So that's going to be d dt of our y prime divided by dx dt again. Okay. So when I do that, oh, let's see what I get. I got to take the derivative of this using the quotient rule. So let me do that over here to the side. Okay, so that's going to be derivative of the top times the bottom minus top times the derivative of the bottom, okay, divided by the bottom squared. Okay, so that's going to simplify to what? 6t squared minus 12t squared, so that's minus 6t squared, minus 24 over 3t squared minus 12 squared. Something feels off. I must have done it wrong the last time I did it. They have things I don't have there. But, oh well. Okay. Just check one more time. Okay, never mind. We're just going to go with it. Okay. So this is going to be negative 6t squared minus 24 divided by 3t squared minus 12. Now, since that's squared here, and I have another one from dx dt, right? 3t squared minus 12, that's just going to be cubed. Okay, so that's going to be dy d2y dx squared. Okay, now one thing I'm going to do, I am going to simplify this so that I can look at the concavity. Okay, so what I'm going to do, I'm going to factor it out. Okay, so let's factor out this negative 6 t squared minus 4 over, or t squared plus 4, sorry, 3t squared. Let's factor out the, I see what I did. Let's factor out the 3. Okay, so when I factor out the 3 here, that's going to be 27. Okay, and then I have t squared minus 4 cubed. Okay, t squared minus 4 is t plus 2t minus 2. This is going to be negative 6 t squared plus 4, 27 t plus 2 squared, I'm sorry, cubed, t minus 2 cubed. Okay, now this is something that, to analyze this is something I teach a lot in college algebra. I'll link for a video for that, for using sign charts, but just quick and dirty, what I do is I'll take negative 2, 2, negative 6 t squared plus 4. 27 is not going to make a difference. T plus 2 cubed, t minus 2 cubed. Okay, 27. Now, 27 is always positive, so I don't worry about that. Negative 6t squared plus 4, that's always negative because of the negative 6. Okay, t plus 2 cubed, that changes from being negative to positive at negative 2. And t minus 2 cubed changes from negative to positive at 2. So you've got 3 negatives gives you negative, positive, negative. So when is it concave up? Again, remember, whenever this second derivative is positive, and that's between negative 2 and 2. Okay. All right. All right. I will see you guys in the next set of videos. Let me make sure this is, because that's not supposed to be including. Okay. I'll see you in the next set of videos. Yeah, that's how it's going to go. All right. See you next time.